So a wide choice is, rather than brushing up everything, to leave some simple part to you completely and and use the available time to discuss more rigorously on the important part. So from that point of view, and based on the students' requirement, we are free for discussion at any time. So if they feel that some part which was assigned to them as a self-learning module is difficult, they can come and discuss at a later time. So the restrictions on poles and zeros, that point we leave for your self-reading, and we go for time domain response from pole zero plot. So now I am sure that the idea is clear for you of the transfer function. Idea is clear for you for the transfer function. We would be more interested in GS, G21S, that is output voltage upon input voltage. Even though there are driving point functions and transfer functions, we are more interested in G21S. So unless otherwise specified, we shall refer that is the gain of output upon input. So from pole zero plot we get an information about some critical frequencies. Again, when we talk of, I cannot avoid the temptation of going in details because these are some very key issues. So we get a function, say for example, if we take this, what is G21S? What is G21S for this? 1 upon S upon 1 upon S plus 1 multiplying by S, what do we get? 1 upon S upon 1 upon S plus 1, leading to multiplying by S in the numerator and denominator, 1 upon S plus 1. 1 upon S plus. Is it alright? So, if you look at this function, what is the zero of this function? Very simple transfer function we have put. HS or G21S what is the pole for this function? What is the pole for this function? S equal to minus 1. S equal to minus 1 is the pole of the function. Is it alright? Yes or no? And what is 0 for this function? Infinity. S equal to infinity is the 0 for this function. Because I think we are one pole zero expert in the class. So, since in the numerator we do not have a polynomial, we have only single figure. So because of that we don't get 0 from the numerator. We get one pole from the denominator. And when it is so to match poles and zeros, we get a 0 gets automatically mapped at S equal to infinity. So at S equal to infinity, so pole is at S equal to minus 1 and 0 is at S equal to infinity. What is the significance of 0 at S equal to infinity? What is the significance of 0 at S equal to infinity? One thing is we go by some brute force method and then we will go by classical method if time permits. At S equal to infinity, I can by brute force method say that this impedance S, this impedance 1 upon S. So at S equal to infinity, this impedance becomes 0 and this remains 1. So we don't get any. So it is eventually a short. as well as zero impedance. Then where we get pole? At s equal to minus 1. At s equal to minus 1 we get pole. What does it signify? At s equal to minus 1 we get a pole. Total impedance? At s equal to minus 1 we see this ratio of output upon input is for the class of inputs e raised to minus st. Also e raised to st is for the class of inputs e raised to st. Then if I apply e raised to minus t, if I apply e raised to minus t, then so pole at s equal to minus 1 means input as e raised to minus t. Input is e raised to minus t. So what output is expected? What output is expected? Then when we get e raised to minus t, pole means infinite output. Pole means infinite output, or it is the ratio becoming infinite. Then you may get a feeling e raised to minus st is a decaying signal. So you are talking about how output is reaching to infinity. I thought that you are talking the ways and means with which the output is reaching to infinity, and we have some alternative explanation. So by formula we get pole at s equal to minus 1. So s equal to minus 1 is e raised to minus t. So e raised to minus t is a decaying signal. Then do you feel that there is something which is confusing? How for a decaying signal output will go to infinity? How for a decaying signal output will go to infinity? Is there any chance, is there any way by which output will reach to infinity? S equal to minus 1 means V in t is e raised to minus t, that's all. So what is happening now? When we look at e raised to minus t, no doubt it's a decaying signal. But it is having very large value also at t equal to minus infinity. It is not starting from t equal to 0. All this discussion on poles and zeros is not in the confined space that you are starting from t equal to 0. A signal of e raised to minus t is always there, means something which was having infinite value, and then what we get these are exactly reverse. E raised to t was 0 at minus infinity, and then exponentially increasing up to infinity as t progresses. And e raised to minus t is exactly reverse of that, 1 upon that. That is very large, infinite at minus infinity, and rapidly decaying exponentially in order to get 0 at t equal to infinity. Both match at t equal to 1. So I hope that at t equal to 0 it is like this, asymptotically approaching 0, and this is asymptotically approaching 0 on this side, like this. So we think of the output getting developed here when this signal was applied, e raised to minus t, which was very large initially. So So if you really apply e raised to minus t as input to this, then you can write a suitable differential equation. You can write a we will, in order to see that we prove what we say convincingly, we can just derive once again. So what will be the case now? It is V in T, it is V O T. What is current? V in T minus V O T upon 1. That is V in T minus V O T. And what is current? dVOT by dt, because this is 1. So now S is to be forgotten. So V in T minus VOT is right, and dVOT by dt is also equal to I. Is also equal to I. So what we get? dVOT upon dt plus VOT is equal to V in T, which is now e raised to minus t. Number dVOT upon dt plus VOT is equal to e raised to minus t. You get this differential equation, and I hope that you might have learned it to solve. And if you attempt its solution, what you get is you get infinite solution. You get infinite solution. For all other inputs, what happens is we get some bounded results. So for this particular one, you get infinite solution. So S equal to minus I again repeat, it's very, the module number 5 and to some extent 6 are difficult to understand, wherein we have to rigorously have brainstorming to understand what does it mean. Right? Okay, so this is the again pole 0 plot, and then we may plot poles and zeros. And then based on the HS, we get the idea of, means the time domain response from pole 0 plot should indicate us, when we get pole 0 plot, just like an expert doctor looking at the ECG is able to interpret the state of the heart. Similarly, by looking at pole 0 plot, you should be immediately in a position to tell how the system is functioning. What is the function of the system? This is one. And what would be this transfer function? S upon S plus 1. We had 1 upon S plus 1 there, and here we have what? S upon S plus 1. So both are somewhat high pass and low pass, we shall come to that. So based on pole 0 plot, you must be in a position to check the time domain behavior of the system. What we mean by time domain behavior of the system? Time domain behavior of the system means how I will be getting the actual signal. At the output. If this particular input is applied, in what way I will get this signal at the output. And then, rather than discussing it in vacuum, we can take an example, and based on that, we should be in a position to find out whether you are able to get the answer. Actually, time domain behavior is inverse Laplace transform. Time domain behavior is inverse Laplace transform. Inverse Laplace transform indicates us in Laplace transform, or in general, have you got a good understanding about the impulse function or Dirac delta function? That is infinite at t equal to 0 and 0 elsewhere. Now let us so how can we find the inverse Laplace transform? How to find? Actually, based on pole zero plot, either by graphical one or by our conventional analytical means, to find out inverse Laplace transform. So in a way, this HS, we did not start with that. I deliberately avoided the discussion. I was always saying that what HS is? HS is the ratio. I am not sure, despite I am trying my best to simplify the contents in teaching, the extent of your learning still remains, what we can say, an unsolved question for me. There are two schools of thought. The HS, if you go to the literature, is the ratio of Laplace transform of output voltage upon Laplace transform of input voltage, or in other words, you can use it to be G21S, gain 21, output upon input. G21S, I try to summarize again. G21S is equal to V2S upon V1S, whereas this is V2T, this is V1T. Is G21 is V2S upon V1S. Whereas, can anybody explain to me how we have computed G21S? We computed G21S by considering the impedances of, for R it is R, for L it is LS, and for C it is 1 upon CS. How we have come to those impedances? We have come to those impedances that if the voltage is of the type e raised to st, then we have a notion of impedance of Ls and 1 upon Cs. So in other words, what we discussed, if I apply an input as e raised to st, if I apply an input as e raised to st, then what the output would be? If Vin is e raised to st, then I am sure I am sure that output would be something into e raised to st. If I apply input as e raised to st, then output would be something e raised to st only, and then I can say that I can take a ratio of v2t upon v1t. Or if v1t is equal to e raised to st, then what I get as v2t is equal to something into e raised to st only, means something into v1t itself, and then this I have taken to be g21s. This I have taken to be g21s. So Laplace transform of output upon Laplace transform of input is same as this. By both ways we can reach there. The question is how you will convince yourself that both ways are equivalent. And then if g21s is one function, if g21s is one function in S, then I may get its inverse. Since it's a function of S, I can have its inverse Laplace transform. I can have its inverse Laplace transform, which is g21t. And what that g21t means to me? What that g21t means to me? Then if I now look at g21s as the ratio of Laplace transform of output upon input, if I look this to be equal to v2s upon v1s, then what is v2s? Is Laplace transform of v2t. What is v1s? Is Laplace transform of v1t. Again repeat. If I am looking g21s as ratio of Laplace transform of v2t upon Laplace transform of v1t, and then if I find inverse Laplace transform of g21s itself, which is equal to g21t, it will be corresponding to the output of this circuit for what input? Now forget about our discussion now. G21 is ratio of Laplace transform of output voltage upon Laplace transform of input voltage. V1t is input voltage. V1s is its Laplace transform. You have perfect pseudo understanding of these terms. V1t, V1s, V2t, V2s, V2s upon V1s, G21s. Inverse of G21s, G21t. So the question is very clear. If G21s is ratio of V2s upon V1s, which is Laplace of V2t upon Laplace of V1t, then if I take its inverse Laplace transform, that is G21t, so G21t will be the output of the circuit itself for a particular input. What is that particular input? I further simplify. G21s is equal to V2s upon V1s. So there will be a situation where G21s is V2s when V1s is 1. When V1s is 1. So if V1s is 1, what is G2s? Laplace transform output voltage. So what is G21T? Inverse Laplace transform of G21S is inverse Laplace transform of V2S itself. That is output voltage itself. So if I ensure that V1S is 1, then what is the G21T is the V2T itself. So G21T is nothing but V2T for that V1T whose Laplace transform is 1. What is that V1T whose Laplace transform is 1? One upon S. No. So find out that V1T whose Laplace transform is of 1 upon? No. What is inverse Laplace transform of 1? 1 upon S. So limits are from what is V1T? Have you heard of this? Delta T. Laplace transform of delta T is 1. Delta T is infinite at t equal to 0 and 0 elsewhere. Delta T is infinite at t equal to 0 and 0 elsewhere. Delta T is the limiting case of a rectangle of area 1. We start with rectangle or square of area 1 or triangle is better proposition actually. A triangle of area 1 and the we can start with rectangle, but triangle is more appropriate approximation. Triangle of area 1, it may have some width, some height. Then we go on reducing the width of the triangle by keeping its area intact. So the tip will, how the tip will move? Tip will move up, come here, move. As it comes, it will move further up. As it comes, it will move further up. So the tip of the triangle will asymptotically reach to infinity. Are you getting me? So a triangle whose area is 1 and whose base width is reducing, by keeping area same, height is increasing, so it's a very steep triangle. Triangle of width 0 and area 1. To be more particular, you can start with this is appropriate or this is appropriate for you to decide. In this case, the width will reduce, it will further increase. So this I think is more balanced discussion. Why we should be favoring on this side. So width reducing, height increasing. This is delta function. Delta function is limiting case of a triangle with its base centered at 0, some width, area 1, base reducing, height increasing, area remaining 1. Then what is 2 delta t? 2 delta t will also be a triangle of area 2 whose base also reducing, but so height of delta t at t equal to 0 is infinite. Height of 2 delta t at t equal to 0 is also infinite, but height of 2 delta t is twice of the height of delta t. So infinities are not unique. I think we discussed sometime in the class. So for this we get Laplace transform as 1. Right? So an impulse is infinite at 0 and 0 elsewhere. So what can be the good example of an impulse? Can you give? Just think for a while. Think from what we can say, some kind of beating each other context. So think of an impulse. So children are having a habit of fighting with each other. So with respect to children fighting, think of impulse. There are few ways. I think we can, being a non-conventional student, it is difficult to describe it in English language. So we can change in mother tongue. समजा मुळे मारत होतो तुम्ही काय करणार एकदा हात पिरगाळतो अशा चिमटे काढणे बुक्क्या मारणे तर हे सगळे जे प्रोसेस आहेत त्यामध्ये जी मारामारीची ऍक्शन आहे इट इज ऑक्युपाइंग टाइम. हात पिरगळतो असं तो कंटिन्यूअस असं दाबून करायचं. तर आता ह्या कॉन्टेक्स्ट मध्ये इम्पल्स काय तुम्ही डिफाईन करू शकाल? वेगवेगळे इनपुट सिग्नल आहेत त्याची आपण एक्झाम्पल्स दिली. तर त्या मारामारीच्या कॉन्टेक्स्ट मध्ये इम्पल्स एक कशाला उदाहरण देते तुम्हाला चपखल बसेल अशा पद्धतीचं?
थोड्या कालावधीसाठी जेव्हा आपण 2 बुक्या मारतो
मुद्दा मांडल्याची आपण सविस्तर चर्चा करू. बुक्क्या मारण्यामध्ये बुक्की मारण्याचा जो कन्सेप्ट आहे जो फोर्स आहे तो असा खूप नसतो. तर खूप जास्त अँप्लिट्यूड आणि खूप थोड्या वेळा करता. तर ह्याचं कुठलं चपखल उदाहरण ते चपखल बसलं पाहिजे. डायव्हर्ट खूप तशी येते आपण डायव्हर्ट होणार फक्त मारामारीचा विषय somebody is coming to the answer. What's that? No, don't see. Even though we are considering the example, even though we are considering example lighter vein, it is being used in order to create an, an everlasting impression about impulse within your mind. So take it in that spirit and don't make fun of it. Anybody? Impulse right. Impulse equivalent of children fight. एक अशी कानाखाली लगवायला म्हणतो आपण. So the theme is that its impact is very large. Its impact is very large. It comes and goes. Its impact is very large. It doesn't remain. So all inclusive. If we think of it in other way, you take a hammer and you are having say steel frame, steel sheet, very thick sheet, have a hammer and have a punch. So impulse is like a punch. Impulse is like a punch, very large for very small time, but substantial area. So what when we consider the quantum effect of that punch, so multiple punches or a single punch, it's a very small time but very large magnitude, in such a way that it is, what is the measure of impact then? Neither the height nor the time, but it's a product. One is very large and one is very small, but their product is a defined area. The product quantifies the input itself. So impulse is very large and that disappears. That completely disappears. It completely disappears. But what happens is, this once is applied here, output will continue forever. In a decaying manner, no doubt, but it continues forever. So what is inverse Laplace now? 1 upon s plus 1? It is e raised to minus t. So when an impulse input is applied, this is the time domain response. This is the time domain behavior or time domain response for impulse input. That is, time domain behavior is the inverse Laplace transform of the transfer function. Time domain behavior is the inverse Laplace transform of the transfer function. Then, so for you to understand these things in detail. It will take some time. You will have to think rigorously further. So next we come at the stability of an active network. One simple example I would like to give. So this only. What is G21S now? What is G21S? What is G21S? It is 1 upon S square plus 1. What is inverse Laplace transform? What is the inverse Laplace transform of this? It is sin t. So what does it mean? Means if impulse is applied, what is your number? 20. What does it mean? That if we apply impulse here, if an impulse is thrusted upon, then it will continue to deliver the output sin t. It is not decaying now. Forever, when an impulse is applied, it will continue to give sin t. Sin t would always be available. Sustained oscillations. We can give an example. You got a tuning fork. When you punch the tuning fork, it starts vibrating. And because of if the tuning fork is to vibrate in vacuum, what will happen? It will never stop. In air, because of some small frictional force and all that, it stops, but it vibrates for quite a long time. It is sustained oscillations. This is having a square plus 1 in the denominator is an indicator of oscillatory nature. So it continues. Right? Okay. So I think it's 2:15 we have time.